Hello guys, we are going to take a minute to go through a couple of additional examples for solving literal equations and working with function notation as it's related to graphs. And these are going to be just some example problems for you guys to consider as we continue to move forward with our study of Algebra 1. Okay, so with solving literal equations, situation we have right here, you can see that it says 4m sub 2. Okay, so that's going to mean that we are going to solve this. We're going to change this equation right here, and we're going to get m sub 2 by itself. So that's the goal. The goal is to get that little piece right there all by itself. And you can see that everything else that is tied with it is tied with either multiplication or, in this case, division with r squared. So I'm going to start by multiplying both sides. I think that's an m sub 1 and an m sub 2. We're going to multiply both sides by r squared. Okay, so we're going to get rid of the divided by r squared. We're going to multiply both sides by r squared. And again, remember, the thing we're trying to do is to get this term by itself when you're solving a literal equation. Okay, so what we have left at this time is r squared times f is equal to g m sub 1 m sub 2. So I'm going to go ahead and divide by g m sub 1 on both sides, g m sub 1, and the g variables cancel, the m sub 1 variables cancel, and you can see that our final answer then is m sub 2 is equal to r squared times f, all divided by g m sub 1. So that is solving a literal equation for a specific variable. Here's an example of what's called the gas law, and you're supposed to get r by itself. And again, remember that anytime we are solving for a variable, we're just getting it so it says r equals, and then everything else is on this side of the equation. Okay, so it looks like I'm going to divide. And let's see, what am I dividing by? I can't see. I'm going to divide by n and t, both sides, n and t. The t's will cancel, the n values will cancel, and my final equation will be r is equal to pv divided by nt. A lot of letters flying around here as you're working on literal equations. Okay, the other thing that I wanted to talk to you guys about today that we kind of brushed over a little bit was this idea of how to use your function notation with a graph. And so I wanted to just remind you of how you could go about doing these types of problems, and remind you that these types of problems have an inside where you're looking at an actual x value whose output is a y value. And it also has this other kind of situation where you have an output, an outside. So this is kind of our inside-outside function notation, where you're given a y value and you have to work backwards to find your x value. Okay? So the way we do this for the inside values is we go to -4, that's going to be our input, and our input we're looking for along our x-axis. So -4 is right here, and so I go to my graph and I go, oh, the output of having x is equal to -4 is going to be a positive 2, so this is just equal to 2. If I go to f of 0, I can see that my y value that is on my graph is also 0. If I go to 3, 1, 2, 3, I can see that the y value is, maybe -1.8 or so. We'll estimate. on that one. And then f of -5, again, we go to that x value of -5, and we can see that our graph crosses at a y value of 0. Okay. Now remember, things change up a bit when we're talking about f of x equals 2. We're trying to find the x value where our output is 2. Okay? So here's a y value of 2, and it looks like we have 2 different spots on our graph that could result in a y value of being 2. It looks like we could get an answer of -4. So x could be -4. But because we have another spot right here, it looks like about a -1, maybe a -0.8. Almost a -1. We'll say a -0.8 right here. So those 2 values, if we plug them in as an x value, we're going to get 2 out as a y value. And then what about this one, where my y value is 0? Okay, so I'm looking at all these places where my y value is 0. It actually happens in 2 places that my y value is 0. It happens when x is equal to -5, and it also happened when x was equal to 0. Okay, so that is kind of how you can use a graph with your function notation. Let's take a look at one more situation down here, and this is going to kind of lead us into some of the thinking that you guys are working on in this upcoming unit, because you have a graph that is in the form y equals mx plus b. Okay, so we know that -4 is our y-intercept, and our slope would be 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And over 1. It's going to be a really, I don't even know if I can make it that steep on this graph. There we go. That looks pretty good. Okay. So remember, when we're thinking about the inside, this function evaluated at 4, what that means is we're going to be plugging the 4 on the inside. Okay, so we get 36 minus 4, which is 32. That is completely off our graph, way up here. So we could plot the point 4, and then we'd have to go clear up to 32, somewhere way up here to plot our point. Okay, so that's what the function s evaluated at 4 means. When I plug 4 in, then the output is 32. Okay, so this is an outside situation right here. Find t. So we're going to find, this is kind of going to be our t value. This is going to be our s of t up here on the y-axis. We're going to actually plug a 23 into what the output would be. Whoops. So we're going to have 9t minus 4, and this time the output is 23. Okay. So if we add 4 to both sides, stick with me on this idea here, because we're still going to be doing a lot of work with function notation as we continue with our linear functions. And we get 9t is equal to 27, and we divide by 9 and get t is equal to 3. What that means, okay, so we're going to kind of come down here. It means that if 3 is our input, then 27, oops, not 27, but 23 is our output. Okay, so really paying attention to when you are given an input versus when you are given an output. Okay, that's an input, this one's an output. All right, guys, good luck with your function notation, and your next video will be about slope and slope-intercept form of your function. All right, good work.